So there's just two last notes that I want to give you on this method. So more types of solutions, I'll call this. So if you have repeated complex roots, combine, use cosine of beta ln x and sine beta ln x with multiply by powers of ln x. So for example, m equal to, let's see, 3 plus or minus 2i repeated twice gives, you've got your x cubed cosine of 2 ln x, your x cubed sine of 2 ln x. That's just the complex rule. And then for the repeated roots rule, you would say, okay, x cubed cosine of 2 ln x times ln x cubed sine of 2 ln x times ln x. So they combine exactly the way you'd expect. If you have combinations of real and complex roots, you just combine them the same way you would with constant coefficients. Just your general solution can have all kinds of roots in it. And then if you have something that's close to Cauchy-Euler but a little bit different, where you would have a sub n times x minus some number x0 to the nth power, nth derivative of y, down through a1 x minus that same number, y prime plus a0 y equal to 0 for constant x0. You're just going to take a similar type of solution, y equal to x minus x0 to unknown power m will work. So for example, if you had 3 times x minus 2 squared y double prime plus 2 times x minus 2 y prime plus 7y equals 0, you would assume y equals x minus 2 to the m and plug in. So those are just a couple final notes for your reference. And because this was going to be a really short video, I went ahead and wrote our wrap up right here. So I'm just going to go back to the start, do that normal talk through of everything, and then we'll do our wrap up. So we learned about Cauchy-Euler equations. I said we would describe the type of problem we have, talk about the general approach and some special rules, do examples, focus on a non-homogeneous problem, and then expand the method in a couple ways. So Cauchy-Euler equations are things that look like this. That's a little bit abstract, so the thing to really remember is that the power of x needs to match the order of the derivative, and then you have a Cauchy-Euler problem. Our approach to solving them is really similar to how we solved constant coefficient problems. We just assume that y has this solution type, and then we plug it in, and we solve for the powers m that we don't quite know when we make that assumption. And just like constant coefficients, there are 3 big cases. We find our, I guess, real values, m1 through mn, then we can go ahead and say that y is given by that solution. But if we have repeated roots, we multiply by powers of natural log x. And if we have complex roots, we multiply by cosine and sine of beta times the natural log x, for beta the imaginary part of our solution. We went ahead and did that first very simple example with two distinct real roots, and we found our solution. And I made a little aside about how this is really similar to constant coefficients. You just need to remember that your auxiliary equation can't be copied directly from these numbers corresponding to powers m like you could have with your constant coefficient problem. So just be careful that you actually get the right equation there. We did a repeated root example, and I noted that you actually know how to derive this repeated root rule using reduction of order. And then we did a a complex coefficient problem. And I think I made a note about how you just have to be careful to remember those natural logs inside the cosines and sines because it looks so similar to what we did before, or not making like e to the alpha x, so then you do x to the alpha x. Just be careful that you copy the exact form these functions should be. Then we did that really long non-homogeneous problem. I just tried to emphasize that non-homogeneous problems have two parts. We just learned a new homogeneous part, and then we did that. And then we went back and did a non-homogeneous part, which was actually an old method for us. And we put everything together at the end. And then just now I told you about these different types of solutions, kind of combining our repeated roots and complex roots rules. And then how this can be generalized to something a little bit more complicated than just powers x. It can be kind of like x minus a constant to some power. So the wrap up here, I tried to summarize what I think we did. So I said we're solving this type of equation, and the phrase to remember so that you can identify that problem is you just think powers of x should match derivatives of y. So you should have x squared, y double prime, x, y prime, so on and so forth. I said it's really similar to constant coefficients. You just have to remember the special changes we make for the functions that you add on for repeated roots and complex roots. And then kind of exciting from this section is that we can solve a more complicated kind of non-homogeneous problem now. But as you saw, it's a really long problem, so you need to just be careful. There's a lot of steps to remember. I tried to highlight a couple of them as we were going through, but this is the type of problem that you now have the tools to do, even though you kind of learn them in separate bits. You can put them together for something very complicated. So your practice problem today is right here. It's going to be to try and solve x cubed y triple prime plus 5x squared y double prime plus 7x y prime plus 8y equal to 0. I don't want you to solve this all the way. Please just stop at the point where you have your auxiliary equation and you know that you would try to solve that, but it's going to be cubic. I just wanted you to get practice to see how that formula for the auxiliary equation goes to higher orders. I don't want you to actually solve a cubic equation. So stop when you get to that place where you know what you would solve for m. So that's everything I have. I will see you in class.